Hey everyone and welcome back to PrepFusion. I am Anish and today we'll start the lecture 6P of this Electrostatics chapter. So we have studied about capacitors, what are capacitors, what are different types of capacitors, we derive expression for capacitors. Also for non-standard shapes, I have given you a few homeworks as well. So those homeworks I will do and then we'll start with today's topic, that is series and parallel combination of capacitors. Also few assignment questions on dielectric strength of capacitors and obviously questions on series and parallel combination of capacitors. So obviously I will go back to the first one. First one was pretty simple. There a isolated sphere was given and you had to find the capacitance of that particular sphere. It was a very old gate question, 1997. Okay, this question was given. Just use the simple formula. You can derive as well. I have derived just before here itself, so you can derive or just directly write down the formula. It's good to remember. Okay, it takes you a very small amount of time and it's easier to remember as well. So 4 pi epsilon r, you put 4 pi and epsilon is, it's in earth, so simply we'll use 8.854 into 10 to the power minus 12 into 10 into 10 to the power minus 2. So you have to take care of the units. What are the units? Convert everything to SI units. Sometimes I will tell you, you don't need to convert as well. Without converting, you can get away. Without converting into without converting the units also, you can get away and get to the right answer. That also I will explain in this lecture itself. So you get your answer as 11.12 picofarad. This will be the answer for this particular question. Okay, a pretty simple straightforward question. Now definitely this question was not straightforward. Okay, this question was difficult and more difficult it came here. Okay, because at that point of time I didn't give you another hint that you had to find out capacitance per meter. Okay, not directly capacitance but capacitance per meter. Now what do I mean by capacitance per meter? What does it actually mean? Now if you didn't know, okay, just pause the video. Let's say I have asked you to find the capacitance per meter. If you don't know what is capacitance per meter, what will you think? What would you think what capacitor per meter means? Now there must be one parameter throughout which everything is same, right? And if I divide by that parameter, I will get my capacitance per meter, right? So I have to divide along some length. Which length should you choose? Along the radius, along the height, along what? If I divide the capacitance, right, along the radius, each surface, right, I will get some different capacitance because here the epsilon will change, keep on changing. That is not correct way. If I cut this along the height, right, if I cut this along this distance height, okay, then this capacitance whatever I will get at here as well, if I cut this distance height, I will get the same capacitance. So that is what capacitance per meter means. It should not vary basically, right? So if I divide it along the height, I will get my capacitance per meter. So basically here capacitance per meter means C by H. Another hint what you can take is they haven't mentioned H anywhere. So obviously it has to be that unknown only because you don't know what is the value of H. So you have to divide that by H and you will get your other value. Okay. So once we solve the question, there you will understand. So first thing, solving from basics, I know you have to understand what is the electric field across this capacitance. It is lambda upon 2 pi epsilon r naught. Okay, then the direction you know, and simply integrate. How to do all this I don't know. I have already explained you how to choose the limits. Also I have explained you. Okay, now you come to this point. Okay, you come to this point. Now here very important, another important point is this, whatever expression this is written, right, epsilon r equals to 10 plus rho divided by rho. Just remember this thing, they have mentioned rho is in centimeters. So whatever you put here, right, that should be centimeters, not meters, because they have defined it such. They have defined as such that 10 plus rho means this 10 is also in centimeters, this rho is also in centimeters. That is a definition. Okay, no need to write meters here because they have defined. So you will write your centimeters and they have provided centimeters only, so you will provide centimeters here. So just be careful. Finally you after doing the integration, it will come out as 10 plus b divided by 10 plus a. Simple integration things, this you can do. Now what you have to do, you have to put the values, like this is actually 2 pi epsilon naught h divided by this, so it is a function of h, but they have asked me to find out capacitance per unit length. So obviously I will divide by h and all the knowns will be present. There will be no unknowns. A, B, and epsilon naught, all values you already know. Just be careful while putting the values here. It should be in centimeters. Because they have mentioned in the question. That's why. Okay. So now if you put the values, you will get the value answer as 435.17 picofarad per meter. Pretty simple, straightforward. Nothing to like say about. But this question was very good. Okay. This question was very good in lot of ways. So another question I gave you, as this question we did, this question as homework I give you, right? This question is also a good question. 2013, this question is also a good question. Here they are asking like dielectric slab is given and the cross sectional area and the how long it is, all those things are given. What you have to find out, they have explicitly mentioned the electric field as well as it is uniform. You might say, sir, here the length is very large than the area. but they have mentioned that somehow they are able to get a uniform electric field. It does not vary with distance, and obviously it does not vary with time as well. So again, all those whatever formulas we derived, those will work here because those were only for uniform electric field. The relative permittivity of the dielectric material is equals to 2. If the relative permittivity of the dielectric material is equals to 2, then you have to find out basically the energy stored in the dielectric. Okay, so how do you go about this question? First thing is, what is the energy stored in a capacitor? It is half CV square. As it is dielectric, right? It is half CV square. So I can find out the E, and from the E I can find out the V, right? What is V? V simply, for a uniform electric field, V is simply magnitude of V into D. Okay, simple constant linear relationship. What is magnitude of V? This, do remember, this is 6 square plus 8 square whole under root. It becomes 10. But what unit is this? Kilovolt per millimeter. So I'll convert everything into volt per meter, right? SI units. So kilovolt to volt means 1010 raised to power 3, and millimeter, 1 millimeter means 10 raised to power minus 3 meters. So 10 raised to power minus 3 is in the bottom. So it will go in the numerator. So overall it will become 10 raised to power 6. So 10 into 10 raised to power 6 volt per meter. Okay, that is the electric field basically. That is the electric field. Okay. So now what is the capacitance? Capacitance, this is for a parallel plate configuration, simply dielectric slab. So it will be epsilon A upon D. Epsilon is epsilon R epsilon naught. So this time do keep this in mind that they have given a relative permittivity, right? So don't ignore it. Okay, I also made a mistake. I ignored it, so my answer was not matching. So you have to like take this permittivity as 2, then this epsilon naught is 8.85 10 raised to power minus 12. Then this is what? This is in millimeters, right? 25 into 10 raised to power 4 is areas in millimeters. So we'll convert this back into meters. Simply multiplying 10 raised to power minus 6 will do. Okay. This is the capacitance basically, and divide by 0.4. This is in meter itself. The distance is in meter itself. Okay, and this is the capacitance, and this is the potential. So if I do all this compute, just put the values in calculator, you will get 88.54 joules. Now if this solution didn't satisfy you, okay, so what you can do is you can do the method 2. Method 2 is simple, without the need of capacitance. What is the fundamental formula of energy? Energy density we know, right? It is independent of anything. Energy density is what? Half epsilon into magnitude of electric field whole square. I hope you remember this, right? So if we do this, they have given me the electric field, okay, and epsilon R I know, and this half is half. But what else do I need? This is the energy density, but I need the potential energy across this whole dielectric. So I will multiply the energy density into the volume of the dielectric. What is the volume? Simply area into the distance, because this is the area, and if I multiply it by distance, I will get the volume. So yeah, this I already know. This is what? Half into epsilon. Epsilon is epsilon R into epsilon naught into E, magnitude whole square. E is 10 raised to power 7 volt per meter. Everything is in SI units. Whole square into area. Area is 25 into 10 raised to power minus 2. So this is the thing basically in meters whole square, and this is in meters as well. So if I put everything, right, I will get my value as 88.54 joules. Now you decide which one is easier. I think this one is simpler, so you can use this without even going to the formulas, or some calculation mistake can happen in the previous method. This method is better. Okay, so yeah, that's how you solve this particular question. Next, I think I give another homework. This one is the last homework, and this one is a bit of a lengthy question, but still nonetheless. So point 1, I think you are able to solve this. This second part will be a bit lengthy. So here what I can say is what will happen, like this we already know, right? Initially they are separate, but they have same charge density. Okay, they have same charge density, but do they have same charge? No, right? Because Q1 will be what? Sigma 1 into A1, charge density, surface charge density into the area, equals to this 4 pi r square sigma. Sigma is same for both of them, right? Sigma 1 is equals to sigma 2 equals to sigma. Okay, not sigma, yeah, sigma only. Now Q2 will be what? Charge present on the larger sphere. It will be sigma 2 into A2, but sigma is same. Sigma 2 is same as sigma. A2 is what? A2 is different, right? A2 is 4 pi into 2r whole square, because the second sphere has 2r of radius. So obviously here it will become how much? 4 into 4, that is 16 times the previous case, right? Not 16, 4 times the previous case. Okay, so it has more charge now. So if it has more charge, what will happen is that after they are connected with a wire, charge will distribute. And how will they distribute? As if they have same potential, because the surface will become equipotential. So here what will happen? V1 dash will be equals to V2 dash. Dash means after t equal to 0, or after connecting the wire, equals to V equals to KQ dash by R equals to KQ2 dash by 2R. Okay, so this is what formula for potential. Although Q1 dash and Q2 dash are different, but obviously the radius is also different. That's how their potential becomes same. So I can directly say q1 dash by q2 dash equals to 1 by 2. This is how also you can find out q1 dash or q2 dash. Q1 dash equals to q2 dash divided by simply 2, half of the second sphere. Whatever charge will be present in the second sphere, it will be half. Okay, first sphere charge will be half. Now I will use conservation, charge conservation. Basically initial charge will be equal to final charge. Initial I had q1 plus q2 charge, final I had this q1 dash plus q2 dash. Q1 dash is this, q2 dash is this only. So q2 dash I will get, because if I add these two, this will become 3 by 2 q2 dash into q1 plus q2. Now what is q1 plus q2 actually? So q1 I have already find it out, right? 4 pi r square epsilon, and q2 is 16 pi r square epsilon. So this whole thing, if I add these two, this will be 20 pi r square epsilon, and if I have to multiply by 2 by 3 to get my q2 dash. So I got my q2 dash. Now what I can say is q2 dash will be actually equals to the charge density after connecting the wires multiplied its own area. This won't change, right? But this will change because charge has changed. So sigma 2 gas, what is this basically? What is 4 pi? What is q2 dash? Q2 dash is this, right? 2 by 3, 20 pi r square. And I will also like few things will get cancelled, and your answer will come out to 5 by 6 sigma. So this is the answer for the first part, that is you have to find out the charge density in the after t equal to 0. Okay, after their connection. What about the charge sigma 1? So sigma 1 sigma equals to q1 by a1, that is the initial charge, because those were same on both the spheres. Charge density was same. So sigma will be equals to q1 by a1, and I need to go solve for the second part. What is the second part? Need to find out the change in energy. For change in energy, I have to find initial energy and final energy. Initial energy is pretty simple. It is simply half. I am writing everything in terms of charge, because charges are given, right? Charge density is given, so I will write everything in terms of that. So it will be half into q square by c1 or plus half into q2 square by c2. Now here, right, I have named this variable a equals to 4 pi r square just for our simplicity, okay? Because in the examination hall also you can do the same, because area I have written it as the area of the smaller sphere, and then whatever will be the area of the larger sphere. If the area of the smaller sphere is a, it will be simply 4 times a, correct? So here this will become 4 times a. And what is q? Q is area times the sigma, initial q, and this also q is area of that particular sphere into sigma. So this area is 4a times sigma, and this is a times sigma, okay? And then if I make whole square, this will become a square sigma square, this will become 16 square sigma square, and overall you will get back this expression, okay? I'm not totally deriving writing everything, but just showing you how to compute, okay? Overall you will get back this expression. Now sigma 1 dash, that is a sigma 1 after their interconnection, after they are connected with the wire, will be q1 dash divided by a1, right? So q1 dash has changed. What is q1 dash equals to? Q1 dash equals to q2 dash divided by 2, okay? That is what I have written over here, q2 dash divided by 2, not here. Here, right, we have derived from the charge same potential concept. We have derived q1 dash equals to q2 dash divided by 2. So just replace q1 dash with q2 dash divided by 2, which is equals to what? q2 dash is equals to what? q2 dash by a. q2 dash by a is simply this thing, right? Sigma 2 dash. Sigma 2 dash is what? 5 by 6 sigma, and exactly that is what is written, 5 by 6 sigma, okay? So this will become 5 by 12 sigma, okay? Now you find will be what? Simply half into q1 whole square divided by c1 plus half into q2 whole square by c2. You can do all this. I haven't computed like to the end, okay? So you can do all this, and you will get your answer as particular something like this, and you can just do the difference of both of them, and you will find out your answer, okay? Numerically it would have been better if I would have given some numerical numerical data, but that's fine. This is also fine. Just like we have just variables here, okay? So now we'll start the concept of series and parallel combination of capacitors. So let's start with the series combination of capacitors. Just hold on a second. Yeah, if I start with the series combination of capacitors, what do we observe? Series, with the parallel combination of capacitors, we'll basically use the boundary conditions. In parallel combination, basic 11 and 12, we know what happens, right? We say that, okay, charges are coming here, charges are getting divided here. So charge is getting divided, potential remains same between these 2 points, and that is correct. That is actually not wrong. That is also a good way to look at it, is that my charge is q equal to c, right? Total charge. But through here q1 charge flows, through this capacitor q2 charge flows. So q1 equal to c1 times v, because the potential difference is same, it does not change. And for the second one, it is q2 into q2 equals to c2 times v, okay? So this is the case. So my q1 what I can say, Q, another equation I know, Q1 plus Q2 equals to Q, right, capital Q. So what will be the C equivalent? So I know Q equals to C equivalent into V. So what is Q? Q is Q1 plus Q2. And what is Q1 plus Q2? Q1 plus Q2 is C1 V plus C2 V. So C1 plus C2 V equals to C equivalent into V. So my C equivalent simply come out to be C1 plus C2, because in case of capacitance, it is the other way around. If you remember, for resistors, the parallel combination, the expression was a bit weird. Here the parallel combination expression is simple, but series combination expression is bit weird expression. Okay, C equivalent is C1 plus C2. That is the equivalent circuit. Okay, but there are other types of combination as well. Those I will discuss. But actually, what is happening inside the dielectric, that this we learned. Okay, fine, in circuit analysis. Okay, but actually, what is happening inside the dielectric? Inside the dielectric, both of these plates, okay, are connected between 2 points, and obviously this plate has some charge Q1 and this plate has some charge Q2. Fine. Okay, electric field is through these 2 plates is E1, electric field through these 2 plates is E2. Okay, and what mean for parallel, well, always understand this, whenever they are in parallel, right, what I know about parallel, voltage is same. Okay, so between these 2 plates voltage is same, between these 2 plates voltage is same. Now if voltage is same, what is the electric field? Electric field is charge divided by the rho s upon epsilon, right? Electric field in this point, in this particular region, right, in the top region, is rho s upon epsilon. So what is rho s for the top one? It is Q by A into B1, because this I can vary, although this doesn't vary, right? This the one dimension doesn't vary. Generally we vary B1, we can vary A as well. Okay, we can vary A as well, but in our case we're assuming that A is constant for both of these, but B is varying, the other one dimension is varying, right? So this is A and B1. Okay, so E1 equals to Q1 by A B1 epsilon 1. Okay, just take any Gaussian surface and you can derive. I hope you understand how am I writing this E1, right, in the top surface. Okay, simply charge divided by the area, rho s upon epsilon. That's it. 2 plates, rho s upon epsilon. Same for E2. Now what is the boundary condition? What is the boundary condition? Boundary condition is that at the interface, right, at this interface, the tangential components of the electric field must be same. What are the tangential components? The whole electric field itself is tangential. There is no normal component. So what I can say is, here no normal component. Component of electric field. No normal component of electric field. Okay, so that is the case. Now here what is the boundary condition? Boundary condition is E2t should be same as E1t. Now in our case, the whole electric field is tangential, so E1 should be equals to E2. So E1 and E2 actually should be same. These two electric fields should be actually same. So what will be different? The charges will be different. If these are different, the charges will also be different. Okay, that will be difference. Okay, so if E1 equals to E2, so Q1 by AB1 epsilon is same for both of them, or epsilon can also differ, right? This medium and this medium can have different dielectrics. This will be epsilon 1 should be equals to Q2 by A B2 by epsilon 2. So obviously you can vary this A as well, but in our case we're not varying, I'm just deriving the expression. You can vary A as well. Okay, that is also fine, that is totally fine. So in this I get the ratio of the charges. How will the charges actually get divided? I think you never knew how the charges were getting divided. Charges are getting divided like this. Q1 by Q2 is equals to A B1 epsilon 1 divided by A B2 epsilon 2. Okay, and what is A B1 and A B2? So if I divide both numerator and denominator by D, what do I observe is this is the expression for C2 and this is the expression for C1. Okay, right? So this will be C1 divided by C2. Simply ratio of their capacitances. Like you can understand from here as well. Okay, simply divide these two expressions, so VV will get cancelled and Q1 by Q2 will be C1 by C2. Okay, you can derive, but anyways, okay, like that also, you can derive like that as well. So this is the first question that I wanted to give you. Okay, first observe that whether the capacitors are in series or parallel. It's difficult to observe here, right? So what I see is these two plates and I have electric field going in this direction, right? Electric field going in this direction, or you can assume this direction as well. So because electric field will always be perpendicular to the plates, so I can observe that electric field only has tangential components and here the two electric fields are same. So obviously what is happening? These two are in parallel because the potential difference are same for the two dielectrics, right? Here epsilon R1 is different, here epsilon R2 is different. Okay, so they have given me epsilon R and they have given me D. So they are asking me what is D2. Very simple. Okay, what do you know? The tangential component must be same. So you will say the tangential D2 flux density must be same, and here the tangential is the electric field itself, total electric field itself. So I will say D2 equals to D1T. So obviously I will write 2 coulomb per meter square, correct? But unfortunately you will be wrong. Why you will be wrong? Because you forgot that this case was for electric field, not for electric flux density. The tangential component of electric field was same. Okay, so E1 equals to E2, correct? And what is E1 in terms of your normal flux density or like flux density? It is if I remember, it is epsilon 1 times D1. This is the case, right? No, it was the case. No. It was okay. Sorry. D1 equals to epsilon 1 into E. So E1 will be equals to D1 by epsilon. Yeah, D1 by epsilon, which is equals to D2 by epsilon 2. Okay. So what do I get? So this becomes what? So now I can equate, right? Now what is my D1? D1 is 2. Epsilon 1 is epsilon naught into epsilon R1. What is epsilon R1? It is 2 equals to D2. D2 is unknown only, and epsilon R2 into epsilon naught. So it is 4 times epsilon naught. So here I can say that my D2 will be equals to what? D2 will be equals to epsilon naught gets cancelled, will be equals to simply 4 coulomb per meter square. Okay, this will be the answer. Okay, not the previous one. So pretty straightforward and simple question. So you can just use the boundary condition. Have I used any new concept? No, just use the boundary condition. So here few things are written for parallel plate capacitors for parallel combination. The voltage across each capacitor is same as the applied voltage for in case of parallel combination. The total charge is the combination is the sum of the charges on each individual capacitors. Okay. To ensure safety, the capacitor with the lowest charge carrying capacity should be used as a reference as it determines the maximum voltage in the parallel arrangement that can safely withstand. Okay. So what do I mean by this? Let's take example. Simple example. Here I have two capacitors, C1 and its Q max is 2 microcoulomb, and C2 its Q max is 1 microcoulomb. Okay, and let's say this has a capacitance of like it will be proportional, right? Q will be proportional to the CV. So let's say it is 1 microfarad and this is 2 microfarad. Or let's not make it directly proportional, let's make it different. Let's make it 2 microfarad. Let's make it 3 microfarad. Okay, so which one will I choose as reference? You will say this has the maximum charge, so I will choose this as reference, right? Maximum 2 microfarad can flow through this. You will say no sir, I will choose both of them as reference. So maximum, what I want to charge can I flow maximum? This has maximum 2, this has 1, so it will be totally what? Q max of the combination should be 3 microcoulomb. Now is this the case really? We will observe this. Is this the real case really? So can 3 microfarad charge be flown? Okay, for this particular combination to flow 3 microfarad charge, 3 microcoulomb charge, what are the individual charges in the capacitance? Now this was the ratings. Okay, this was not a charge distribution, this was just the ratings. So like in your phone there is some rated voltage, right? For like 10 volts, 5 volts, like that. It's not the actual voltage that is being getting applied, it's just a rating of that particular thing. So this is the rating. Okay, nothing, this is not the division. Capacitance I have been given, they are fixed. Okay, so according to the capacitance the charge will get distributed. So according to you chose the maximum limits for all of them. So you chose 3 microcoulomb. So if I choose 3 microcoulomb, what will happen is that how will the charge get divided? So Q1 will be what? Q1 will be simply equals to I know Q1 by Q2 is C1 by C2. So what is C1? C1 is 3. Q2 is 2. Sorry, C2 is 2 microfarad, right? So 3 by 2 simply. So I know Q1 will be equals to 3 by 2 of Q2. So I'll use simple charge conservation. What is charge conservation? Conservation, it is Q1 plus Q2. And I am actually flowing the maximum amount of charge because you have told me that, okay, sir, I will take the maximum ratings of each of them and I will add them up, because in parallel I know charge gets divided. So maximum 3 microcoulomb I will flow through the combination. So Q1 plus Q2 should be equals to 3 microcoulomb, which is actually equals to what? Which is actually equals to this, right? I will replace Q1 with this particular thing. So 3 by 2 Q1 plus Q1 equals to 3 microcoulomb. So what does, out of this thing, what does Q1 is? Q1 is 5 by 2 Q1, and Q1 comes out to be 6 by 5 microcoulomb. Now here I observe a problem. What is the problem? Q1 max was actually 1 microcoulomb, correct? If you observe here, Q1 max was actually, okay, so not Q1, sorry, this is what I found out. Sorry, this is Q2. Sorry, this is Q2 actually. Sorry, this is Q2. So Q2 max is what? Q2 max is actually 1 microcoulomb as specified by the manufacturer. But what are you doing? You have given 6 by 5 microcoulomb. Will it be able to sustain that amount of charge? No, it will get damaged, because there will be huge amount of electric field and the dielectric will get damaged. So I cannot use it. So what went wrong here? What went wrong? You did this simple addition, right? This is where you went wrong. You will choose whichever one has the lowest maximum charge. You will choose that as a reference. Now choosing that as a reference, you will be able to find out how much maximum charge actually I will be able to apply with the combination. Okay. So now we will come to the series combination. So in case of series combination, things are again simple. If you just do the circuit analysis point of view, right? We know charge is equals to CV, and I know same charge will flow through a whole of this combination. So charge is constant, but potential gets divided. So basically I know Q1 equals to C1 times V1, and Q2 equals to C2 times V2, and I know Q1 is equals to Q2 because in series circuit charge is same. So obviously I can comment the C1 V1 equals to C2 V2. So this time potential difference is different. V1 by V2 equals to C2 by C1 simply. Okay. So how do I find out the combination? What is the combination? So from here what I can do is, what else I know, V1 plus V2 equals to V, this total potential, right? V1 plus V2 is equals to V, correct? So I can say what is Q equals to CV. Okay. So what I will do, I know I will make this ratios constant, right? Q equals to CV. So if I divide the whole thing, what is the common thing here? Charge is the common thing, right? If I divide this by C, right? If I divide this by C, why should I? Yeah, 1 by C equals to V by Q. Okay. So what is V by Q basically? This is V by Q, right? So 1 by C is what? V by Q. So what is V? V is V1 plus V2. Okay, and Q is same. Q is same for everything, that is equals to Q. So I can further derive this, that your 1 by C equivalent will be equals to V1 by Q plus V2 by Q. And what is V1 by Q? What is V1 by Q? V1 by Q is simply what? Is 1 by C1, right? If I put the C1 here, and this V1 by Q1 is simply 1 by C1. So this becomes 1 by C1 plus 1 by C2, and you can connect infinite number of capacitance in series. They will be following this relationship, okay? It will be followed. So it will just like a parallel circuit in case of resistors, just the opposite. But what is actually happening inside the combination, inside the dielectrics? So if I have a series combination, right, and electric field, I hope you know how to compute the electric field here. In this, whatever the epsilon 1 is, electric field will be Q1 by A times B by epsilon 1. Okay. So here this areas are same. Okay. The distances are different. This time the distance is variable. I will always choose one unit as variable. Okay. This is for parallel plate combination. I will show you for spherical capacitors and cylindrical plate capacitors as well. Don't worry about that. So here what I am observing is that E1 equals to Q1 divided by AB epsilon 1. E2 equals to Q2 divided by AB epsilon 2. Okay. So here the important point is that again I will choose the boundary condition. Which boundary condition I will choose now? Pause the video and tell me. So I will choose the normal boundary condition, right? Because the interfacing medium is normal to the electric field. So what is a normal boundary condition? Normal boundary condition is basically what? That the electric flux density must be same. Okay, electric flux density everywhere must be same, normal to the interfacing medium. Here if you observe, what tangential, do I have any tangential component of electric field? No, I don't have any tangential component of electric field. I only have normal component of electric field. So what I can say, that E1t equals to E2t equals to 0 whenever for series combination, right? E1t, E2t are 0. Okay, and what other thing I can comment? Very beautiful I can comment is how many of this dialectics you put in series, right? What will be common? Common will be the electric flux density. D will be equals to D1 equals to D2 equals to D3. N number of dialectics you put in like in between the two plates, right? Outside two plates, all of them will be same. Okay, all of them will be same. They will not change. But what will change? Obviously the electric field will change. With respect to what? With respect to the electric permittivity, right? Permittivity of the medium. So this I can replace, D1 I can replace with epsilon 1 E1, epsilon 2 E2, and from there you can simply solve. This will be equals to epsilon 3, this is not vector quantity, sorry, epsilon 3 E3, and this will go on, right? So this is what is happening. So here, like some same problem only, same example, but this time what is this combination? This is a series combination. Why? Because the distance between the two plates, I have two dialectics between the okay, and the potential difference is not same. Between here to here there is some potential difference, and here to here there is some other potential difference. So can we find the electric field at the second dialectic slab? Again I'll use the normal condition. I know D1n should be equals to D2n, which is a complete electric field. So what is D1n? It is epsilon 1 into E1. It should be equals to epsilon 2 into E2. So what is epsilon 1? Epsilon 1 is 2 into epsilon naught into E1. E1 is 2 equals to epsilon 2 is 4 into epsilon naught into E2. Okay, so E2 is equals to 1. Okay, 1 volt per meter, because here the unit is volt per meter. I will choose the same unit, that is 1 volt per meter. So not that difficult to understand. These are pretty simple question only. There is no normal component, right? There is only tangential component, because electric field will flow from either from here to here or either here from there. Sign doesn't matter. I'm just concerned with the magnitude. So here few points are written for series combination. All capacitors in series have same charge. This is the condition one. There they had same voltage. The net charge on the combination is the same as the charge on any one capacitors, because net charge is equal to same only. So here the net voltage was equals to the voltage on any one of the capacitors. For same operation, capacitor with the lowest breakdown voltage, thus the lowest Q max should be considered as reference. Okay, so here also it is not totally correct. Here okay, if Q max is lower, if the lowest charge is flowing, right? Yeah, if through the whole combination lowest charge is flowing, then yeah, that will be considered as reference. But here, right, something is wrong here. I will just rewrite this statement. I will just check once. Okay, this statement is not completely true. Lowest potential maximum, as it determines the maximum potential. Yeah, actually, yeah, this statement is correct. Actually, here what is happening is that if you observe, what is the V max I can apply to this particular capacitor? So there I derived it a bit wrong. Here, what is the V max that I can apply? V max is what? Q equals to CV. So V will be equals to Q by C. So in this case, it is Q max by C. C is constant, that is 3 by 2. Okay, and in this case the V max is in this case the V max is Q max divided by C, 2 by 3. 2 by 3 volts. Okay, so this particular thing, Q max, Q equals to CV. Yeah, this is telling me that I can apply maximum 2 by 3 amounts of voltage, and this particular combination is telling me I can apply, sorry, this is not 3 by 2, sorry, this was the other Q max, right? This is not this Q max, this is the Q max, right? This is the Q max of this particular capacitor, so it is 1 by 3, 1 by 2. So this is telling me I can apply maximum voltage of 1 by 2. This is telling me I can apply maximum voltage of 2 by 3. Which one will you choose? Which one will you choose? The lowest. Because if I apply, like this is 0.66, right? 0.67. If I apply 0.67, this will get damaged. Because this is telling me I can only apply 0.5, but I have applied 0.67. So this will get damaged. So in case of parallel combination, I will choose the lowest voltage. Okay. Capacity should be used as a reference. In case of parallel combination, as voltage is same, I will choose the voltage. Okay, as the voltage is same, I will choose the voltage as reference, as voltage is same for everything, right? In parallel, voltage is same for everything. So I will choose the voltage as reference. Okay, so there I derived a bit wrong. But in case of series, what will I choose? I will choose the charge as a reference because charge is same everywhere. So I will choose the charge as reference. So I will pick and choose each and every one of them. So let's say what can be the Q max of the combination? Q max of the combination will be minimum of Q1 max, Q2 max, and so on. Okay, and so on. What about the parallel combination? This is for the series combination. I will choose the minimum of this. Okay, so if two capacitors are contained in series and one has 1 microcoulomb of maximum charge, another one can actually sustain 2 microcoulomb of maximum charge, which one will you choose? You say I will choose 2 microcoulomb, but if through the series combination 2 microcoulomb charge flows, obviously it will damage the first capacitor. I cannot choose 2 microcoulomb. I will only choose 1 microcoulomb. So that is the same for here also. Okay, in case of parallel combination, I will just write down the formulae. Charge will change to voltage. Why? Because voltage is common for everything now. Voltage is same. V max of the combination will be minimum of V1 max, V2 max, and so on. Okay, I will choose whoever can sustain the minimum rated voltage. That one will be my reference. Okay, so I hope you got the point of parallel and series combination for picking the reference. Okay, you don't want to. Main thing is you have to ensure safety. You don't want to damage your device. So with that you can derive anything, right? I've just told you how you can derive. So this is a good combination of different types of capacitors. So there is a series and parallel combination of capacitors, right? So how will I solve this? So there are two ways to solve it. You can solve it using Lenz's method as well, or you can directly solve it using simple circuit analysis. So how will I go about it? Simple circuit analysis, what you observe is these are the two plates, okay? And here I can observe that the distance, perpendicular distance is changing. So obviously these two are in series because here same electric flux density is same throughout this, right? So here what is happening, these two are in series. So let's assume due to epsilon 1 there is capacitance C1 and epsilon 2 there is capacitance C2. So these two plates will be simply in series C1 C2, okay? And the third plate, if I observe, has the same potential difference as the combination of these two. So they are connected in the same endpoints, right? So it will be in parallel with the series combination of C1 and C2. So this is the combination basically. So now always do this. Always derive the circuit expression of whatever given in the picture. And now it is simple, right? This you used to solve in your childhood. So C equivalent will be what? Simply series combination of these two. That is C1 C2 divided by C1 plus C2 plus parallel. Because this is in parallel, I will simply add this two. Okay, in capacitor things happen oppositely, and you have studied network enough, so I will not go too much in depth. How is it? Am I adding? How am I doing the C1 C2 by C1 plus C2? Okay, you have studied network. So C equivalent is this. So if C equivalent is this, what can I say? I can find out C1 C2 all them individually. So what is C1? Basically C1 is epsilon 1 A by D1, correct? A1 by D1. So what is A basically? So here, right, this is 10 centimeter and this has 20 centimeter square conducting plate. So the width has changed, width has halved. So overall this was 20, this was actually 20 centimeter, but here I have half the width. So obviously this will become 10 centimeter square now. Okay, so area will become 10 centimeter square now. So this will be epsilon 1 will be have they given me, yeah, epsilon r1 auto they give me. So this will be 1 times epsilon naught into 10, because area is halved. Why? Because the length has been halved, right? One of the dimensions has been halved. this divided by this in centimeters, so I will convert this into meter actually. This will be 10 raised to power minus 2 whole square, correct? Yeah, divided by the distance. Distance is in again 10 centimeter. This is the perpendicular distance, right? So 10 into 10 raised to power minus 2. Okay, so this will be some value. I will just derive them later on. This will again be here. Epsilon r2 has changed, the area remains same, and the distance also is same, right? So just this will be what? This will be 2 times the c1, because like I will do some shortcuts here. This will be twice the c1. Why? C1 is same, just epsilon r2 is changed from c1, right? That's it. You can go and check the question. What about c3? C3, this area is again half, okay, but this is 20, so this distance has been doubled. So this, if this distance has been doubled, so obviously this also will be twice of c1, right? But what is the epsilon r3? Epsilon r3 is 4. So okay, this will be 4 by, like you can write the simple expression as well. You can take the ratios as well. 4, like 4 times c1, but the distance also has been doubled, so 4 by 2. Okay, everything else will be same. Everything else will be as this only, because this particular 10 I have written 2 times this, and here instead of 1 I have written 4. So exactly that is what I have replaced here, right? That's it. And everything else is same as c1, so I will write it as c1. So this also will be 2 times the c1. Okay, so overall what will be my capacitance? C equivalent will be what? First of all I will compute this. So this is c1 into 2c1 divided by 3c1 plus 2c1, because this was c3. So this equals what? This equals c1 gets cancelled. This is 2c1 divided by 3 plus 2c1. So this is 2c1 into 4 divided by 3. Okay, so what is c1? Now I will replace c1 basically. So that's how you do the calculations and reduce your calculations, right? Reduce your strain on the calculators. So this actually is epsilon naught. Have they asked us to? Yeah, right, in picofarad. So this will be 8.854 into 10 raised to power minus 12, and one of the 10 raised to power minus 2 gets cancelled here. So I have only 10 here. This 10 gets cancelled. Only 10 raised to power minus 2 is left here. Okay, 10 raised to power minus 2 is left here. That's the only thing, right? So I can simply compute this. I'll just quickly compute this. This is 2 times 4 divided by 3 into 8.854, and this actually is 23.61, and 10 raised to power minus 2 is also there, right? If 10 raised to power minus 2 is also there, this one will come out to be 0.236 picofarad. Simply this will be the answer. This will be the C equivalent of this particular expression, right? So you can solve these things. Okay, another question, very simple. In JEE mains they have given okay, the composite parallel plate capacitor is made up of 2 different dielectric materials of different thickness. As shown, the 2 different dielectric materials are separated by a conducting foil F. The voltage of the conducting foil. Okay, so here they are actually asking me what is the voltage of the conducting foil with respect to some common ground. So I will assume this as ground. What is the voltage of this conducting foil? How do I find out the voltage of the conducting foil? So this one you can solve using simple maths. What you can do, I know that this is a parallel plate combination, right? So here what do I have? This is C1 and this is C2. Okay, and here I have basically applied a voltage of 100 volts. This is a common with respect to this. They are asking me to find the potential here, right? So they haven't mentioned reference. I will choose the reference as this. Okay, always the lower potential of the battery we choose as reference. So they are asking me to find the voltage of this conducting foil here, right, at this particular intersection. So what do I need to do? I can apply simple maths, right? What do I know? They are actually in series. although it is seeming that they are in parallel, they are not in parallel, they are in series. So if they are in series, the charge should be same, right? So what is the charge? Charge is Q1 equals to Q2 equals to C1 V1. Okay, this potential difference, right? V1 is this potential difference. Okay, remember this. V1 is this potential difference, V2 is this potential difference. So what will this become? Sorry for waiting. So now what other things I know? So C1 C2 I can individually compute it, so, right? C1 C2 I can individually compute. So what is C1 basically? C1 is actually equals to epsilon 1 into the area. Area is same, they have same area, right? They have same area, they have not mentioned anything, just dielectric materials are different and the thickness is different. Okay, so area is same, this will be A divided by the distance, that is T1. Okay, and C2 is epsilon 2, area is same, divided by T2. So can I find out the ratio of these two things? What will be C1 upon C2? C1 upon C2 will be epsilon 1 upon epsilon 2 into T2 upon T1. So what is the ratio basically? Epsilon 1 upon epsilon 2. Epsilon 1 upon epsilon 2 is basically epsilon R1 upon epsilon R2. So epsilon R1 is 3, epsilon R2 is 4. So C1 upon C2 is 3 by 4, correct? It is 3 by 4. What about the T2 upon T1? So this is T2 upon T1. T2 upon T1 is 1 by 0.5. I don't care about the units because they automatically get cancelled out. So it will be 1 by 0.5. So this will be 3 by 2. Okay, so that is the case here. So here if I am observing C1 by C2 equals to this 3 by 2. So I know this. Now can I write down the ratio of potentials of V1 by V2? So what will be V1? What will be V2 by V1? V2 by V1 will simply be equals to C1 by C2, right? Because charges are same. C1 by C2, which is equals to 3 by 2. So V2 is equals to 3 by 2 V1. And what other equation I know? I know that V1 plus V2 is actually equals to 100, correct? This whole potential will be equals to 100 itself, KVL, simple KVL. So I will replace this, right? I will replace V2 here with 3 by 2 V1. So it will be 5 V1 by 2 equals to 100. So V1 is equals to 40 volts. Okay. So V1 equals to 40 volts. This is what I got. But what is V2? V2 is 3 by 2 of V1. So it will be simply 60 volts. And that is what I require, right? I need VF. VF is with respect to ground, which is simply equals to V2, right? So it will be 60 volts. 60 volts will be your answer. Option B will be your answer. So this came in JEE Mains. I saw this question, but this can come in your examination as well. Okay, this is a very simple question. This can come in your examination. Calculations are simple, but just that will you be able to solve this or understand this concept? Okay. So this question is, this came on GATE actually, something similar along those lines. They've given you the two combinations. Okay, first case and case 2. You have to compare the case 1 with case 2 and find out the capacitance for case 2. Okay, with respect to case 1. So I will give you this as homework. This you can do it. I have done good enough practice to have the confidence to say that you will be able to do this by yourself. Okay, so yeah, that is how you do this basically. That is how you solve this question. Now let's come to the other question. This question. Okay, yeah, this question is actually pretty good. Okay, this question is also not that interesting, because same thing only. A capacitor is made of a metal dielectric having epsilon r equals to this have a dielectric strength of 50 kilovolt per centimeter. The permittivity in the free space is this. The rectangular plates have this length. The maximum electric charge in the capacitor. So I will solve this question because this is pretty simple, but I haven't yet solved in front of you these type of questions, so I will solve it. So capacitor is given, okay, and the dielectric has an epsilon r relative permittivity of 2.26, okay, and a dielectric breakdown strength of 50 kilovolt per centimeter. So E breakdown, E max, right, is 50 kilovolt per centimeter, but I want to convert this into SI units. So how will I write it? I will write this 50 into 10 raised to power 3 is kilo and divide by 10 raised to minus 2. So overall this becomes 10 raised to power 5. The permittivity of the free space is 8.85 picofarad per meter. So this though already we know, this is talking about epsilon naught, 8.85 picofarad per meter. This one we already know, right? Minus 12. So they make get intentionally makes the question bigger with information that you already know to scare you, okay? 10 raised to minus 12 farad per meter. If the rectangular plate have a width of 20 centimeter and length of 40, so the rectangular plate width is 20 centimeter and length is 40 centimeter, okay. So what will be the area? Area will be simply 40 into 20, so it is 800 centimeter square, which in meters will be 10 raised to minus 2. So 8 into 10 raised to minus 2 meter square, okay. Then the maximum electric charge in the capacitor. Have they given us the they haven't given us the this thing. What have they given? What have they not given us? They haven't given us the distance, perpendicular distance between the plates. But do I actually need it? Do I actually need it? If you remember, what was the expression for the electric field here? What was the expression? It was electric field was equals to rho s upon 2 epsilon or epsilon, right? Because due to this plus positive, I will get rho s upon 2 epsilon, and due to this negative, I will get another rho s upon 2 epsilon. So overall, I will get rho s upon epsilon. Okay, so that is the thing here. So this becomes what? What is rho s? What is rho s? Rho s is the charge, surface charge density. So total charge divided by the area, Q upon area. What is the area? Area is A times P, right? Or I can write it simply area divided by the epsilon. Okay, this is the electric field. Now here if I replace everything with maximum, because these things are constant, charge will change. If E becomes maximum, charge will also become maximum. So I will replace this thing with E max will be equals to Q max. We're just concerned with the magnitude. We're not concerned with the direction right now. Q max divided by AE. So what is my E max? E max is 50 kilovolt per centimeter, which I have already written here, right? 15 to 10 raised to power 5 in SI units. 50 into 10 raised to power 5. And Q max, I need to find it out. Divided by area. Area is 8 into 10 raised to power minus 2 into epsilon. Epsilon is epsilon r into epsilon naught. Epsilon r is 2.26. Okay. And epsilon naught is 8.85. Weird numbers. 8.85 into 10 raised to power minus 12. Okay, so basically what everything becomes here, I will just compute this whole thing and I will find out the values. So if I just compute it, 50 into 8 into 2.36, not 2.36 or 2.26, 2.26 actually, 26 into 8.85, what's it, 50 into Okay, I'm not using the geek calculator properly. 2.26 into 8.85. This is total 8,000. Okay, 8k, and this is 10 raised to power 5 and 10 raised to power minus 3, and this also gets here, and 10 raised to power extra cube I will add. So overall this will become 8 q max will be 8 micro coulombs. So this will be your answer. The maximum charge that can be applied in this capacitor is 8 microcoulombs. So this question also come, this type of question also come very simple, that it will be 8 microcoulombs. Okay, option C will be correct answer. Okay, so this one you can I will solve. Actually this is a good question, so this one I will solve. So 3 capacitors are given. Okay, C1, C2 and C3, whose values are 10 microfarad, 5 microfarad, 2 microfarad respectively. So C1 is, I will just write down here. Okay, C1 this is 5 microfarad, C2 is 10 microfarad and C3 is 2 microfarad. Sorry, C1 is 10 microfarad, sorry, this is 10 and this is 5. Okay, so here what I can say, I need to find out and the breakdown voltages are given as 10 volt, 5 volt and 2 volt respectively. So this has 10 volt of breakdown voltage, this has 5 volts of breakdown voltage, and this has 2 volts of breakdown voltage, just same as their like capacitance numbers. For interconnection as shown, the maximum save voltage in volts that can be applied across the combination and the corresponding charge stored in the effective capacitance across the terminals are respectively. So they are asking me what is the Vmax and Qnet. So how do I identify the maximum voltage? So first of all you have to identify how are they connected. Okay, so I can observe that these two are connected in series, and for series what remains? Same charge. So I will say that in the top I will write this as one case. Okay, one combination. Okay, let's first do it for this combination 1. Now for combination 1, Q max, because charge is same, right? Maximum charge that I can apply will be the minimum of Q2 max comma Q3 max, right? Because this is C2 and C3, correct? So in the combination 1, what is Q2 max? How do I find out Q2 max? Q2 max you can simply find out by doing Q equals to CV and CV, because for maximum charge I need maximum potential, right? Maximum potential, rated potential. Capacitance is a independent parameter of potential charge. First lecture, okay, before this lecture what you learned, capacitance is an independent parameter. So for me to find out Q2 max, I have to get V2 max. Okay, and V2 max is given basically. So Q2 max will be equals to V2 into C2, V2 max into C2. So it is 2 times 2, so it is 4 microcoulombs, minimum of 4 microcoulombs. What about this? What about Q3 max? Q3 max is how much again? Okay, sorry, I made a mistake. This is Q3 max actually. Q2 max I haven't computed. So Q2 max is what? Again V2 max into C2. So V2 max into C2 is 25 microcoulombs. 5 volts into 5 microfarads is 25 microcoulombs. Okay, so you get 25 microcoulombs. So I will choose the minimum of this. So which one is the minimum? Minimum is this. So I will choose this. So this will be 4 microcoulomb. Okay. So this is the maximum charge that can flow through this top. Okay, through this top. Now what about the potential? Now if maximum charge is this, what is the equivalent capacitance of the top? C comp 1. Okay. C comp 1 is equals to C1 C2 divided by C1 plus C2. They are connected in series. So I hope these things I don't have to stress on this. So C1 is how much? C1, these are constant, right? This is 5 into 2 divided by 7. So this becomes 10 by 7 microfarad. farad. Now they are asking me what is the maximum potential that I can apply. So what if the maximum charge, this is the maximum charge that can flow. So I will let the combination 1 flow maximum charge 4 microcoulomb. So for that particular charge, how much potential I will get? Why am I concerned about potential? Because I want to consider this case. C1, this is C comp 1. This case I want to consider. This is a case of parallel combination. In case of parallel combination, what do I see? I see the case that my V maximum that I can apply for comp 2. Okay, this is for combination 2. The maximum potential that I can apply is how much? It is the maximum of the potential that can be applied in combination 1, V max comp 1. Just ignore my namings now. Comp 1, comma, the maximum potential that can be applied at C1, Vmax C1. Okay, so what I can say is that what is the maximum combination here? For I need to find out this Vmax. Right? How do I find out Vmax? I will just let the maximum charge flow. Because what do I know? V comp 1 is what? V comp 1 is simply C1 Q equals to C1. So Q1 by C1. Like if I just break down this V comp 1, right? V comp 1 is what? This is C2, this is C3, and some charge Q is flowing, right? So it will be plus minus V2 plus minus V3, correct? So V2 plus V3, and what is V2? V2 is simply charge divided by the capacitance, because Q equals to CB. So this will be C2 plus Q equals to C3. Now these are constant. The potential will be maximum when the top are maximum, basically Q max. So I will replace this by Q max. So V comp 1 max is Q max by C2 plus Q max by C3. Now what is the maximum charge that I can actually flow through this combination so that none of them gets damaged? That is what I found out in the previous case, 4 microcoulomb. So that I will replace here. Okay, so it is taking me time to explain, but trust me, when you learn this method, right, it will not take you much time. Okay, why am I stressing so much in this type of method? Because educators, I have seen many educators teach, but it's a lengthy process. Okay, and you will get confused. But I have tried to mention everything very clearly. What you need to check. I have also written the mathematical expression, maximum, minimum, all those things, so that everything is clear on your head. So this is what this becomes. Q max is 4 microcoulomb divided by the capacitance. C2 is 5 micro, and 4 micro divided by C3, that is 2 micro. So this becomes how much? This actually becomes 4 by 2, that is 2, and this is 0.8. So this is 2.8 volts. So V comp 1 max is 2.8 volts, and V 1 max is how much? V1 max, have they mentioned V1 max? They have mentioned V1 max, right? Because C1 has a maximum voltage of 10 volts. So for this whole combination, V comp 2 max, I need to choose the minimum, right? I have written minimum, right? Oh, sorry, I have written maximum. Sorry. This should be minimum, right? Sorry. Obviously, I will choose the minimum. If I choose the maximum, it will damage the other one. Okay, so that's why I'll choose the minimum. So minimum of 10 of this combination. What is the combination? Maximum is 2.8 volts, comma 10 volts. Correct. That is the maximum for the capacitor 1. So if I choose the minimum out of this will become 2.8 volts. This is the V comp 2 max. Okay, so this is the 2.8 volts basically that I get. So this is actually the answer. This is the actual answer. This is the maximum voltage that I can apply. If I apply some voltage above this, what will happen? basically this, right, more charge will flow, and that will actually damage the capacitor. Which capacitor will it damage? It will damage the C3 capacitor, right? Because C3 has the lowest charge that it can flow. So C3 will get damaged. So this is the maximum potential that I can flow, that is 2.8 volts. So A and C can be correct. What about the this case, right? What about this case? So what about this second option, that is the charge? What amount of charge will it actually store? So obviously from here we have already calculated what is the amount of charge they are storing. So each of the if I flow maximum amount 2.8 voltage, right? Each of them are actually storing 4 micro coulomb of charge. Total 8 micro coulomb of charge they are storing. Okay. So QC2 equals to QC3 for rated condition is 4 micro coulomb plus 4 not 4, sorry, only 4 micro coulomb, right? And what about QC1? How much charge is the C1 capacitor storing? So I can simply do this, right? C1 times V1. What is the maximum charge that I can what is the maximum potential that I can apply across the 2 points? This, right? This is the maximum potential above which the device will get damaged. So obviously it will be C1 is how much? 10 microfarad, I believe. Yeah, 10 micro. This is 10 micro, right? 10 micro times the maximum potential 2.8. Obviously, okay, it's fine. C1 can take 10 volts of rating, right? C1 can take 10 volts of potential difference. But the top combination, this VComp1, right? This cannot take 10 volts. So you say, sir, I can eat 5 bananas in one day. Okay, I can eat 5 bananas in one day, but your brother cannot eat 5 bananas in one day. So if I bought 10 bananas, okay, then both of you combined together will not be able to finish the whole 10 bananas, right? Because you will be able to finish 5 bananas, but your friend, let's say, your brother, let's say, finishes 2 bananas, but still 3 bananas are left. Okay, so that's excess. So obviously this cannot sustain that potential. This can sustain, that is fine, but this top combination cannot sustain. So this will get damaged simply. Okay, so it will be 10 times 2.8. It will be 28 micro coulomb. So what will be the QNet? QNet will simply be QC1 plus QC of the combination 1, right? Why? Because this combination 1 is connected in parallel. And what does this combination 1 possess charge? How much charge does it possess? 4 microcoulombs. How much charge does it possess? 28 microcoulombs. So these two are in parallel actually. These here, right? C1 and C2 are in series. So they have same charge, 4 microcoulombs. So QNet will be QC1 plus Q combination 1, that is 32 microcoulombs. Or you can do it using method 2. Okay, this is the method 1. And like for finding the maximum potential, right, I will recommend you use that method only. Don't use any other method. Okay, that is the best method that you can use. What you can do is method 2 is what? Method 2 is, if I have to find out QNet will be simply C equivalent into V, correct? And I know what potential I'm applying. I'm applying 2.8 voltage. So what is C equivalent? C equivalent will be C comp 1 plus C1. What is C comp 1? C comp 1 is C1 C2 divided by C1 plus C2, that is 10 by 7. 10 by 7 plus C1, that is 10 micro. So 10 by 7 plus 10 micro into potential. Potential is how much? 2.8 potential I am applying. Okay, so this will come out to be 80 by 7 into 2.8 micro coulomb. So this actually is 0.4. So this actually comes out 32 microcoulomb. So this is the easier way which you can do, or you can do it using the previous method, because there you actually have written down the charge expression previously. You were just using it. Okay, you are not calculating it from scratch. Okay, so this question is pretty good. If you couldn't understand, please go through this question again, and this type of question can get asked. Okay, they can twist the question and they can ask difficult questions from this as well. Please fundamentally remember these two things. What are these two things? Always in parallel combination, maximum potential will be the minimum of each of the capacitances. Minimum potential of each of the capacitances, like maximum breakdown voltage that I can apply of each of the capacitances. It will be the minimum. For series case, maximum charge that each of the capacitors can flow will be obviously the reference will be what? The minimum out of this. Because obviously if one capacitor has 1 microcoulomb maximum charge, it can flow. Other has 2 microcoulomb. If you say I will choose this 2 microcoulomb capacitor, and if you in the combination, if you leave 2 microcoulomb of charge, what will happen? It will damage the other capacitor, right? And you don't want that. You don't want to damage the capacitor. So obviously you will pick 1 microcoulomb, so that 1 microcoulomb charge will not damage this 2 microcoulomb charge as well, 2 microcoulomb capacitor as well, and obviously it will not damage because it is the maximum rated capacity that this capacitor is flowing. Okay, so I hope you get the point. That's why I choose minimum of charges when series, and when parallel I will choose minimum of voltages. So that was the thing. Let's come to now a bit of different topics, that is capacitance of different type of configurations. So the part 1 of this is most important one. Okay, just before this, whatever you saw is the most important one. This is also important, but questions that can come from this topic, right, have lower amount of chances than the previous one. But obviously if you are targeting rank 1 or something, like rank under 100, you have to study everything. You cannot skip anything. So first of all, the capacitance of a spherical conductor. We know what is the capacitance of a spherical conductor, right? Now this can have two parts actually. Like I will talk about the series and parallel combination of spherical conductors. So in spherical coordinate, I know there are two things that can vary. Okay, radius, obviously already I am varying the radius, right? Through the radius, the dialectic already is varying. Okay, so what are the other two components that can vary? Phi can vary and theta can vary. Okay, now can you tell me what are the limits of phi? Limits of phi is from 0 to 2 pi. Like, why am I saying all this? Just to like explain you basically how to remember the expression for series and parallel combination. That's it, right? Nothing else. What about the theta? Because there is like, it's very difficult for me to like explain in visualize everything in front of you. You have to, for this I will recommend you remember how am I telling it, remember it that way. Okay, else like it will be very difficult for you to visualize. Okay, and theta, how does theta vary? If you remember, theta varies from 0 to pi. And one other thing you have to remember is that your theta, right, there is another thing with theta, that is r sine theta. Okay, and with phi we have only 0 to 2 pi. So what we'll do is basically these things you remember. Okay, these things you remember. With theta you will always write sine theta, and with phi it will be from 0 to 2 pi. I know it is difficult to remember, but you have to if you want to get a good rank, you have to. Now there can be variations along few directions. If there is variation along r, okay, along radial direction, then how will the capacitors be connected? So let's say I have one capacitor here, which another spherical capacitor here. So in between these two, they have a combination of like they have a permittivity of epsilon 2. Then I have a third spherical conductor which have a dielectric permittivity of epsilon 3. So if I am moving in the radial direction, what will happen? First, due to these two capacitors, what will be the due to these two conductors, spherical conductors, what will be the capacitor? It will be 4 pi epsilon by r1 minus 1 by r2. I hope you already know this, right? This we already know. For the third case, you will just write the capacitor C3, which will be between this and this, right? Then this and this. So it will be simply 4 pi epsilon 2 1 by r2 minus 1 by r3. Okay, this is the C2. Now how are they connected actually? If you observe here, right, how will my electric field flow? Electric field, right? Electric field will flow like this, correct? Electric field will flow like this, and electric field is always in the normal direction. Electric field is normal direction to the surface. So what boundary condition I will apply? Normal boundary condition. What is the boundary condition? D1n equals to D2n equals to dot 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 dot. I will go on. And when does this boundary condition gets applied? When things are in series. So obviously here capacitors will be in series. Okay, simple point. When this boundary condition will get applied when they are in series. So simply C equivalent will be C1 by C2 plus C1 plus C2. Okay, if it is radially, if the medium is varying radially, right? Medium means the permittivity. This medium is epsilon 2. This medium permittivity is epsilon 3. If it is varying radially, this is not epsilon. This is not epsilon 2, epsilon 1 and 2. Okay, so then we can do this, right? Next is if the medium is varying along theta direction. What do we mean by theta? So this is my z, right? This is my z, correct, if you remember. And if my medium is varying in this direction only, right? It is not varying actually radially, it is varying in medium. It is varying in theta. I hope you like for me to visualize this, it will be very difficult. Okay, but I will try my best. So this is my z, okay, plane. And if this thing is varying, if the medium is varying in the theta direction, along theta everything is same. Okay, so from epsilon 1 I am going to epsilon 2. Yeah, sorry for the interruption. So what I was telling is, now we will go back to this. Okay, now we'll come back to this because here bit of difference is there. I visualized how it is varying, but obviously it is not possible for me to explain everything. So what I will do, we can break this formula down. We can analyze this further. So this I can write this like this. This is equals to 2 into 2 pi epsilon by 1 by r1 minus 1 by r2. So here what is happening is, like, I will just show you two things. One thing is, if I integrate sine theta d theta from 0 to pi, okay, what will I get? So that is one thing. And if I integrate my d phi from 0 to 2 pi, what will I get? Like, I hope you remember, your theta only varies from 0 to pi. Okay, so here this will be what? This will be minus of cos theta, and minus of cos theta, if I'll put cos of pi minus cos of 0, so it will be 1 minus of minus 1, so it will be totally 2. So this 2 is actually coming due to this thing. Okay, this integration is coming due to this thing, and this 2 pi is coming due to this integration. Okay, so please, you have to remember these two. Unfortunately, I couldn't find any other way. Now if here I am varying my medium along theta, okay, I am varying along theta, then what I will do, from the positive z axis, this is my epsilon 1, and from the positive z axis up until theta equals to alpha, my permittivity is epsilon 1. Then from alpha, theta equals to alpha, to theta equals to pi, my permittivity is epsilon 2. And obviously it will be symmetrical about the what? About the z axis, right? About this z axis, or what can I say? What is this plane? This plane is like, okay, this is a perpendicular to the xy plane, right? So about the z axis, this would be mirror image. So here also this will be epsilon 1, and here also this will be epsilon 2. From this is what? This is minus alpha. Okay, minus alpha. So it is mirror image about z. So I hope you get the point. So what I will do is, I will write C1 equals to, if I am varying along theta, I will write C1 equals to integration from 0 to alpha sine theta d theta. Just how I got this formula, right? Just like this. Okay, and other part I will write as constant. What is the other part? 2 pi. Now epsilon here is epsilon 1. From 0 to alpha I have epsilon 1. Epsilon 1 divided by 1 by r1 minus 1 by r2. I'm just telling you how you can memorize the formula. We don't have any other option. Okay, and these questions most probably won't get asked, but this, if they get asked, you have to answer, and this is the way only which I can simplify the difficult things. Okay, so this expression comes out very weird. No need to remember the expression, just remember this. Okay, just remember this. So this will be 1 minus cos alpha into 2 pi epsilon divided by 1 by r1 minus 1 by r2. Okay, what about C2? C2 will be from alpha to pi, because theta like higher limit is pi, right? So if there are more mediums, you will just write those limits, right? And at the end, the last limit will be pi. Okay, this will be sine theta d theta into 2 pi epsilon 2 divided by 1 by r1. I will just reduce the size of all this. R1 minus 1 by R2. Okay, so this also becomes, this becomes this, right? This becomes cos alpha minus 1, cos alpha plus 1 into 2 pi epsilon 2, and the same thing only. So this will be same only, just reduce the size. Okay, this C2, and if you observe carefully what is happening, actually these are in parallel. Why these are in parallel? Because the tangential electric fields are equal now. Okay, because electric field through this, right, here there is a tangential boundary. If I see electric field here is, let's say E2, electric field here is E1, right, there is a tangential boundary, right, because along the theta it is a tangential direction with respect to r cap, AR cap. Okay, so here this is E1. E1 is tangential right now through the interface, right? E1, and this is E2. So E1 and E2 are tangential with respect to the interface. Hence, obviously, we will apply the tangential boundary condition, and hence they are in parallel. Okay, hence they are in parallel. That's why the equivalent combination comes out as C1 plus C2. I hope you get the point. Again, if if I am if the division is along phi, okay, this time it will be more simpler. I don't have to explain much. So just remember this. One thing you remember, that what is a medium. So if my theta is from 0 to alpha, medium is epsilon 1. That's why I write epsilon 1 here. If my theta is from alpha to pi, my medium is epsilon 2. That's why I write epsilon 2 here. Okay, these are the two things. Now if my medium division is along phi, so if I am dividing along phi, so from here to here it is epsilon 1, and this whole thing, right, this whole thing, I will just say this whole thing, just try to draw this thing out. I know this will be very difficult for me to explain this thing. Okay, this whole thing, right, this whole thing is from alpha. This is phi equals to alpha. This whole thing is basically, it's not theta actually, sorry, here this is phi equals to 2 pi epsilon 2. This whole thing is medium 2 and this whole thing is medium 1. Okay, I am varying along the A rho cap direction, and A rho cap is again tangential to AR cap direction because electric field is in AR cap direction. So again the interface again is what, tangential to the interfacing medium, hence that's why again this will be a parallel combination. So now what I'll do, I will just simply integrate with respect to d phi. So my C1, I will write all the other things. What were the other things? C1 was equals to integration from 0 to alpha of d phi. What was the other thing? It was 2, right? 2, and what is epsilon? Epsilon 1, because from 0 to alpha my epsilon is 1. So from 0 to phi equals to alpha, it is epsilon 1 divided by, again, 1 by r1. Okay, sorry, 1 by r1 minus 1 by r2. Correct. So this one I will reduce the size again, and what will this result be? This will be 2 alpha epsilon divided by the same thing only. Okay, just remember alpha is in radians. Okay, don't forget to put alpha in radians. This you have to remember, right? C1 will be this. What about C2? What about C2? C2 will be same. Okay, just I will reduce the size a bit more. This also will reduce the size. C2 will be same. Just here, what will be the difference? I'll just show you the difference. The limits will change basically, and this will become epsilon 2, and this will also change. So here this will be C2. So this will go from alpha to 2 pi now. So limits of last limit of phi is 2 pi. 2 pi, this will be epsilon 2. So this will become 2 pi minus alpha times 2 epsilon 2. Correct. And this bottom is same only. So here just one thing you have to keep in mind is that this time my phi is varying from alpha to 2 pi, and between alpha to 2 pi my epsilon is, my medium permittivity is epsilon 2, and also keep in mind that your phi is in radians. Okay, phi is in radians. Just remember this, alpha is in radians and phi also, like all in the expression it is alpha written, so alpha is in radians. Okay, please do keep this in mind, alpha should be in radians. Again, it is parallel combination because we are talking about tangential boundary condition. Okay, so with respect to this, Can you solve this question? If the figures represent the cross section area of two spherical capacitors, determine their capacitances. Okay, so here once I am varying with respect to what, I will not say with respect to what I am varying. Here also I am varying with respect to something, I will not say it. Just read the question, try to understand, because in the gate exam as well, they will not be there to explain, okay, with respect to what I am varying. Just the question will be written and you have to solve. So I will not solve it now. I will solve it in the next lecture with all the other homework questions. We will not solve many questions in this lecture, right? So next lecture will be mainly for question solving. So this question I am giving you as homework, and this question also I am giving you as homework. This is just a simple question, okay, brain teaser. This is not with respect to the previous, like no link with the equivalent capacitance like spherical conductors, but still there is some link, so I will explain that as well. Don't worry about that. Okay, so this question also you can solve. This is again a brain teaser type of question. Okay, you can go and solve this question, and we'll solve all these questions. We'll solve in the next lecture. Okay, so now let's come to cylindrical capacitor. So same thing will happen for cylindrical, but as things are very simple in cylindrical coordinates, because one of the coordinates is same, right? The coordinate on the z axis, that is height, is same as the Cartesian coordinate. So things become more simpler here. Things are not that difficult as the previous case, as the spherical case. So things will be easier. So you will be able to understand this better. Okay, remember, we only apply this formula for rho L equals to constant. If the rho L is not constant, right, we have to solve using basics. This capacitance formula I already know, right? So here what I can observe, this 2 pi. This 2 pi is for what limit? Again, this 2 pi is for the limit of phi, right? Phi is varying from 0 to 2 pi for d phi. Okay, 0 to 2 pi. So this 2 pi is for that limit. So if I am varying my medium across phi, I will use this limit. So step 1 is good. What is this h for? This h is actually for the limit of z. Okay, because z is varying from 0 to h. Okay, so I will do gz 0 to h and I will get back this thing, right? So but in what direction my electric field is in the aero cap direction. So if electric field is in the aero cap direction, and if I am varying my medium in the aero cap direction, what combination of capacitor that will be? That will be series combination, because electric field same direction, my interfacing medium is also in the same direction. So obviously normal components will be same. And what is the normal condition, normal boundary condition? The electric flux densities must be same. So that is exactly what I am doing. This is a normal boundary condition, right? So medium division along rho, nothing will change, right? Nothing will change, everything will be same, just they will be in series. Things will be very simple, because C1 will be this combination, okay, and C2 will be this combination. Okay, so it will be 2 pi epsilon 1 h divided by ln r2 by r1, 2 pi epsilon 2 h ln r3 by r2. Okay, so C equivalent will be C1 C2 divided by C1 plus C2, simple C equivalent. And this I hope you know how to compute, because along h nothing is changing, along arrow I am changing. So this formula you know. So between R1 to R2 my permittivity is epsilon 1, that's why this formula is written. Between R2 to R3 my permittivity is epsilon 2, that's why this formula is written. Okay, simple series combination. And here my, what I can say, electric field is in aero cap direction, and interfacing medium surface, interfacing surface vector also has aero cap direction. So basically what I can say, the normal components dn1 equals to dn2 and so on, right? They must be same. Okay, that is the case. Now what about the other two cases? Other two cases will be parallel, because here if I observe, now if my medium is varying along phi, now it is much more simpler to understand, visualize, because let's say this is some epsilon 1 medium, right? Now if it is varying through phi, so phi from 0 to alpha, okay, let's say some phi, or like one directly say from 0 to phi itself, 0 to phi, my medium is epsilon 1, and from phi to 2 pi my medium is epsilon 2. So you can simply use this integration sign, right? What have I done? I have just kept everything, okay, in sync. Basically epsilon 1 h ln r2 by r1, these are constant, right? These will not change. What has changed? Just this thing has changed, right? Integration from 0 to phi d phi, correct? This thing I have written here. And for this bottom one is also the same. Here integration limits have just changed, so this have changed to phi to 2 pi, okay? So but this will be epsilon 2 as well, right? This will be epsilon 2 as well. This will not be epsilon 1 anymore. Okay, so just remember this thing, that phi is in radians. Always remember phi is in radians, and simply you will get back to this expression, and from here you will get back to this expression. And here what I observe is that my electric field is in this direction, right? Electric field is in this direction, okay, and my interfacing medium is tangential to the tangential to it. So obviously this time I will use tangential boundary condition, that is E1t equals to E2t. Okay, that is what I will use. So as I am using tangential boundary condition, what does it mean? It means they are in parallel, because a tangential components, whenever they are in tangential, that means they are in parallel with each other. That's why the equivalent combination will be C1 plus C2. Okay, simple as that. And if the medium division is along Z, it is even more simpler. So as we move along, we are like getting more simpler. It is like between this to this, right? So if I divide this along height, so along this division I have epsilon 1, and along this division I have epsilon 2. Okay. So here okay, but these are same only, but this will be epsilon 2, right? Yeah, this should be epsilon 2, this will not be epsilon 1, this will be epsilon 2. So here what will happen is everything else will be same, okay, just this time the dz is varying. So what will happen this time is my 2 pi epsilon 1, because I am at the top side, ln r2 by r1. What I am varying, my height is varying from 0 to h1, and in this case dz, and in this case my height is varying from 0 to h2. Okay, so like that's pretty simple, right? And again I can observe that my interfacing medium is what? Interfacing medium is this, right? So here what is happening? I have electric field in this direction, and for the top one electric field in this direction. Again tangential, hence tangential boundary conditions. Hence simply what will happen? I will use the concept of parallel capacitors. C equivalent will be C1 plus C2. Okay. So with the help of this, again, can you solve this question? Now you might say, sir, this is the same question as the previous question. But no, just read the questions properly, you will be able to understand. I will not solve it. I will solve all these questions in the next lecture. So like this is also another question. This also is simpler question, and this has been asked. So okay, so they I think they will not ask for spherical, but they can ask cylindrical. There is a high chance for cylindrical, and understanding cylindrical is not that difficult. So you will be able to understand this cylindrical concept. It's not that difficult, but you should study everything. I have taught you in such a manner that you will be able to understand every single thing. Okay, although I told you to memorize that thing, but how to memorize also that I have told. So how to easily memorize that, right? Because many educators, they will just tell you the formula and that's it. I tell you how to remember that formula as well. Okay, so yeah, I will solve all this question, don't worry about this, in the next lecture. And in the next lecture we'll learn a bit about dialectics, and with the help of that we will actually end our capacitors chapter. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.